Thank you for coming to my talk this fine Thursday afternoon. My name is Jagain Sundar, and I'm CTO of WANDisco. In addition to a nice-sounding name, WANDisco actually stands for something. It's Wide Area Network Distributed Computing. As we go through the talk today, you'll find out why we think that wide area network distributed computing is such a critical part of big data infrastructure. The topic today, of course, is going to be global Hadoop, storage and compute challenges in multi-data center deployments. So let me start by stating what I think is pretty clear so far. Hadoop has outgrown single data center deployments. Almost all the enterprises looking at deploying Hadoop have multiple data centers, and its data is produced in all of these data centers. They're rarely passive standby ones, or at least there's a compelling need to make all data centers fully active. Analytics that's compiled using data from one data center is not really useful. You want aggregated analytics over all the data collected from all these data centers. Let's start by looking at storage. HDFS, of course, is the most popular storage platform for Hadoop applications today, and it was designed as a single data center distributed file system, originally conceived by Google, but then a fine implementation started at Yahoo, and that's what is mostly in use today. If we were to take the naive approach and look at running HDFS over a wide area network, the first thing that people might say is, why don't we just drop some data nodes in a different data center, connect to a name node that's active in the main data center, and we're off to the races? Well, it turns out there are two problems with that. I will talk about the single name node issue a little while later in the presentation. But the reason that this architecture doesn't work is that data nodes heartbeating over the wide area network is very prone to failure. So the name node might consider data nodes as offline or unavailable, even though they are. This causes massive disruption in your main data center's Hadoop. The second reason this doesn't work well is that the write pipeline, or the client writing to data nodes, that whole system has to now run over a wide area network link. That makes it very fragile. The write pipeline is the most critical component of clients being successfully able to write to HDFS. And a fragile write pipeline means you will lose data straight away, right at the ingest point. So there are a few workarounds that people have tried, and they're still in use. One of them is a periodic copy system like DistCP. DistCP was inspired by the Linux program rsync, which basically copies files from one file system to the other. Now, DistCP extended that concept to Hadoop and ran these copy processes in a MapReduce job. So that consumes system resources, your cluster resources also. The other workaround that's fairly popular and also prone to its own set of failures is parallel data ingest. You feed the data into a multiplexer or a load balancer of some sort sitting in either your DC1 or DC2, and that load balancer sends it to both data centers. Again, you have a set of challenges, including your data ingest system now becomes a huge point of failure. The three challenges that you will encounter when it comes to multi-data center deployments is availability, consistency, and complexity of management. Solutions such as DistCP do not scale linearly when it comes to management complexity. So let's talk about DistCP for a bit. So it's a copy system that you run once every hour or 15 minutes or whatever frequency, and it runs as a MapReduce job, divides the work into various mappers, and copies the files that were newly created over to the other data center. The DR, or disaster recovery data center, is read-only. Make no mistake about that. If you have some other process that writes to the DR data center, you have an out-of-sync problem that you cannot recover from using DistCP. What also happens is that you'll notice over time the two file systems diverge. Now, this may not sound like a big deal, but if you have 4 or 5 petabytes of data, reconciling differences and having the owners of those files deal with lost or possibly different data is a giant nightmare in terms of administration. I mentioned manual and labor intensive because it really becomes too hard to manage. It uses the network in a very spiky manner. In other words, when it's run once every hour, you need a huge amount of bandwidth. When it's not run, the network, wide area network, is basically idle. Now, parallel data ingest has its own problem. Your load balancer is now a single point of failure. You could put more systems into that. You could use a Kafka or another Hadoop cluster, but now you've just multiplied your problem. You have the need to keep that cluster up all the time. You have the need to keep the synchronization from that cluster to your 2 clusters also active all the time. It's not practical at all, simply stated. So I want to address one more issue which we consider a serious problem in Hadoop, which is the name node and all its high availability solutions are active standby. You have a single active name node. You can have 1 or more standby name nodes. If the active were to fail, the standby takes over. The clear problem here is that the standby is essentially wasted resources. You do not have the capability to have clients talk to the standby name node and get service from those. This we consider as a problem that is solvable using the same technology that we use for solving wide area network Hadoop. It's, of course, bottleneck in terms of performance, and it works only in the LAN by virtue of its dependence on Zookeeper. The vision that we have for Hadoop is that name nodes should have multiple active servers. There should be 3 per data center, possibly multiple data centers having the same metadata. The value of this is that you have a single file system that is consistent and strongly consistent, and replicated across multiple data centers. There's load balancing because a client can connect to any of the name nodes and get service. Resiliency is, of course, very high because failure of a single name node or even a complete data center is a non-event. Consistency across all of these name nodes and data centers is an important aspect of this. This goes back to our original technology, the wide area network distributed coordination. Again, loss of a complete data center should be a non-issue. And more importantly, we want all parts of your Hadoop cluster. Every data center should be active. You should be able to run read and write jobs against any of the nodes in any of your data centers. I highlight the differences between a standard DR type solution against an active data center based solution that we offer. So one of the things that we really think we need to address for enterprises to easily deploy Hadoop is 100% uptime in all data centers. HDFS needs to run across multiple data centers because you are ingesting data from multiple sources. You want to run your analytics against all of those. This should not cause an increase in administrative burden, and resource utilization should be maximized. You cannot afford to run half of your cluster nodes in standby mode. Again, this is a pictorial depiction of what I've just talked about. So let's go into a little bit of a technical overview of what Vandisco offers. I'd like to take a brief moment to describe what our company does and what we're based on. As I said before, Wide Area Network Distributed Computing is the name of our company, and our technology, our core technology, is an implementation of this distributed coordination algorithm called Paxos. We've extended it to run across the wide area network. Now, We'll go into a little bit more detail about what Paxos is. We are listed on the London Stock Exchange. We had a very successful IPO several years ago, and the proceeds of that IPO were used to build out our big data products, and now we're seeing huge uptake in the financial industry in our big data products. Here's a depiction of a small subset of our customers. So storage, what is it that we offer and what is it we think is desirable for a big data system? It's a strongly consistent replicated data across multiple data centers. I keep saying strongly consistent because ours is not an eventual consistency system. There is at no point in time different views of the data in different data centers. You cannot have a certain variable X with value 2 in one data center and 3 in the other. Eventual consistency systems work in that manner. For the most part, they're somewhat inconsistent. If you can tolerate that, then you're good with that. But we believe that that's unacceptable for most practical use cases. That's why I say strongly consistent replication of data across multiple sites is the single most important thing when it comes to running Hadoop in multiple data centers. We have a few products that address problems in the storage area. Nonstop Hadoop, or Nonstop HDFS, is our enhancement to HDFS to enable operation over the wide area network. We'll talk about how we run the right pipeline in one data center and we ingest in multiple data centers in a little bit. This is a solution that's perfect for pure Hadoop deployments. We also have a product called AutoStore, which is a Hadoop-compatible file system that integrates storage of different types. HTTP, CDH, Isilon, S3, you can have all of these or any of these in data centers. We offer a single, unified, strongly consistent view of the data using our Hadoop-compatible file systems. So your ingest and analytics applications talk to our AutoStore layer, and the data is replicated with strong consistency between these disparate storage systems. It's ideal for mixed environments. You can mix different versions of the same distro, different distributions, and so on. Let me go into a little bit more detail about the architecture of Nonstop Hadoop or Nonstop HDFS. The two storage products I mentioned, AutoStore and Nonstop HDFS, have essentially the same characteristics, and a lot of this applies to Nonstop, to both products. So in data center 1, let's assume for the moment that you're ingesting data or your ingest program is running in DC1. The metadata, that's the file creation operation or the directory maker operation, is coordinated using our Paxos engine across all of these data centers. So the metadata is visible to all of these data centers in a consistent manner. When it comes to the data, we do not want to run the pipeline across the wide area network for reasons that I mentioned earlier on. We really want to restrict the ingest process to a write pipeline in one data center to make that robust and make sure that the client that's writing data doesn't experience failures. So the file is created, the data pipeline is established within the data center of origin, the client finishes its write. Now every time a block is completed, we have an extension to the standard HDFS block replicator called the WAN block replicator. What the WAN block replicator does is pushes a single copy of that block across the WAN to the other data center. When the block lands in the other data center, the normal HDFS block replicator looks at that and figures out that it has inadequate blocks. A new pipeline is established to bring the replication level up to the desired levels in that data center. What we've accomplished by doing this is we've got a consistent view of the data from a naming perspective at all times. When the data is ingested, robustness of client is preserved and normal HDFS semantics are still preserved. So your applications run pretty much unaltered in this distributed data center manner. Now, the important thing is I've described just data ingested in one data center. Remember, both data centers are active. You can ingest data in your DC2. That'll get replicated in exactly the same manner running in reverse to the other data center. We have had much success running this across many data centers. Let's talk about the distributed coordination technology for a moment. This is core to our intellectual property. So what is Paxos, and why does distributed coordination even factor in this conversation? Let's consider something like quantum computing. It's way out in the future. If you have a piece of information available at one server, and at the same instant, if you can have that information available at a second server using quantum compute, for example, what you have is two servers with exactly the same data. Now, if one server were to fail, it's a non-event because the other server can continue servicing clients. Well, we don't have quantum computing, but what Paxos offers is the next best thing. This is the only mathematically proven algorithm for reaching consensus among a network of unreliable processes. So what is consensus? It's basically agreement between 3, 5, or 7 servers as to a specific value of some kind. This gentleman, Leslie Lamport, wrote the Paxos paper almost 20 years ago, and it languished for a while because it's a very complex algorithm that's really hard to implement. But our chief scientist, Ala, took a few years off from work to implement this algorithm from scratch, and he extended it along the way to work over wide area network. That's the core of our intellectual property. This offers the strongly consistent replication characteristics that is visible in all of our products. At the core is this strong implementation of Paxos. There's no restriction on distance between data centers. This is not a EMC SRDF type solution where blocks are replicated so long as it's within 50-mile distance from DC1. Let's take a look at how a Paxos-based quorum system works. It runs in majority quorum. There's a fixed number of participants. A majority of them must agree on it before a value is accepted for all of the servers. Let's say there are transactions 168 and 169. There's a proposal to make a transaction 170. I'll talk about Paxos roles in a bit, but let's assume that one of the clients proposes a change. It could be make dir/a or create file. That becomes proposal 170. The other two servers agree to that, and that turns into a transaction 170. At this point, all three servers apply that transaction, so they're exactly the same. They contain exactly the same state. This is how we're able to keep strongly consistent views of the data. Let's assume for a moment that node A is offline or unavailable, either due to hardware failure or network failure. Node B continues to operate. It makes a proposal 171. Since B and C are running, they get a majority quorum. They continue to operate. Proposals 172 becomes agreement 172, which is a transaction, so on and so forth. Let's say that A comes back now. What you can do at this point is play back the agreements 172 and 173 and bring back A to where B and C are. At this point, it's fully recovered. It's keeping in sync with the other servers, and it can start providing service as well. You can also have a situation where a system is completely failed. In that case, you bring in a new system. We have management tools to bring it up to the state in one bulk instead of having to run through every transaction, which could be time consuming if your system's been up for a few years. Now, AltoStore is our Hadoop compatible file system. It's the same principles I described in Nonstop HDFS apply to AltoStore also. It's a file system interface to ingesting and running analytics. All HCFS compatible applications like MapReduce, Yarn, Spark, HBase, all of these will operate on top of AltoStore just fine. The underlying file systems can be CDH in one data center, HTTP in another data center, and Isilon in a third data center. You can even have Amazon S3 as a storage in one of your zones or data centers. The advantage to that is that if you have a spiky workload where you need to spin up 1,000 VMs once every week to do some compute, you do it on the zone or the data center that's Amazon S3. Data is strongly replicated across all of these systems, and you will have the results published back into your in-house Hadoop. This is a pictorial depiction of that. We have AutoStore servers that provide strongly consistent replication. All of the notes that I made regarding nonstop HDFS continue to apply. Your metadata changes are synchronously Paxos algorithm-wise replicated. Data operations complete in one data center, then they're replicated off to the other data centers. Let me recap our storage benefits. We have continuous availability with maximum performance and scalability. 100% of your cluster is utilized. You have both data centers or multiple data centers running active read and write jobs where you can submit MapReduce or Hive or any queries. Ingest can happen and will happen in multiple data centers. You can configure advanced features such as selective replication, so only portions of your data are replicated out of specific data centers. If you have a banking application that has regulatory requirements such as this data cannot be exported from this country's data centers, you can implement that using selective replication. Here's a number of use cases which we think are valuable to our customers. This is mostly from feedback from customers. Disaster recovery with multiple active data centers is the most obvious one. You can have different zones or data centers with different types of hardware, so you can restrict your memory-intensive applications to one zone and your general-purpose MapReduce applications to the other. There's a number of these which we can go through as we go along. So we've talked about storage, which is the basis for all things Hadoop. What about compute? There is an interesting problem with compute that can be solved with distributed coordination again. I want to go into a little bit more depth here, but essentially what I'm trying to solve is you've got compute frameworks in different data centers. You've got the data replicated, and replication is using WAN links that may have bandwidth limitations. So what you ideally would like to do is run through your entire compute in the data center where the data is available. How do you get to that? So let me do a quick recap of MapReduce. I think MapReduce is a subject that has been beaten to death in various forums. So I'll keep myself brief, but MapReduce is a two-phase compute system where mapping essentially is run on thousands of processes. It does filtering and sorting. Reducing does summing operations. In this particular example, I have 26 reducers that are reducing by first name, and mappers are run one per HDFS block. The key takeaway I want you to take from this is that each reducer must talk to every mapper. So if you have 1,000 mappers, whether they're active or they're finished, the reducer has to talk to the results of each of those mappers before it can do the summing and produce a result. What does that mean in terms of multi-data center deployments? Basically, what it means is you cannot run map in one data center and reduce in another data center. Remember, I talked about selective replication where you may have data that cannot be exported. Well, what you really need to do is run the first phase MapReduce entirely in that data center, replicate the results of that, and aggregate or collate the results elsewhere. Yes, go ahead. Yes. No, the results are on the local file, but you use a web server to get access to it. So the reducer has to talk to the results of that mapper before it can do the summing. And the point I'm trying to make is that it's a many-to-many connection system. The network is really exercised hard when you try and run reducers to mappers. And that is a connection that you don't want over the wide area network. So you really want to run the entire MapReduce in one data center, and the results of that can be used by other MapReduce processes. If you have Hive jobs, a sequence of MapReduce jobs may be produced as a result of a query. And that query can be run in different data centers, but each MapReduce must be completed in a single data center. You can also have Uzi, which is a workflow scheduler, run different MapReduce jobs in a sequence. But what you want is all of that MapReduce to be treated as a single unit of compute. What we want to do with compute is a product called Data Center Aware Yarn, which is to extend the philosophy of bringing the compute to the data by adding the notion of a higher level layer, the data center. In this picture here, I have two data centers with our storage technology spanning across those, be it nonstop HDFS or AltoStore. We also have two different compute frameworks, two different yarn instances running in each of the data centers. But at the time of job submission in any of the data centers, we intercept the job submission. We know where the data is. We can look in the underlying storage system, our file system. We can find out whether the input paths are all available in DC1 or DC2. We will schedule that job on the yarn in the data center that has the data. So there is a guarantee that your data center will be active. There's also a guarantee that the jobs will find the data where they are running. Once the job is done, the whole MapReduce philosophy is that you may take a big data set. Weblogs is an example that I'm going to talk to later in this talk. If you have a 60 or 100 gigabyte weblog and you run a MapReduce to look for 404 errors, that is probably going to be a few gigabytes at most, hopefully if your website is even somewhat functional. You may want to replicate that 4 gigabytes from each of the different data centers and aggregate at that point. That makes it a much smaller WAN link utilization. Eventually, your 60 gigabyte input weblog files will get replicated elsewhere, but the fact is that if you were to run in a very clever manner, scheduling the jobs where the data is available, you can get collated or aggregated results much before all of the data has been replicated to every site. Correct. No. They don't know about 2 yarns. They submit the job to 1 yarn framework, which is what we intercept, and we know which yarn to submit the job to. So the user don't need to be aware of 2 yarns running or multiple yarns running. Correct. That's exactly what we do. I wouldn't call it load balancing because it may not be a balanced load. We do intelligent scheduling. We know where the job's data is, and we run the job in that location. Yes. Yes. And it's done using distributed coordination, so it's strongly consistent. You won't have Mickey Mouse stuff like the job running in 2 places and overwriting results. All of those inconsistencies are out of the picture. We do a really good job of that. So it's interesting, right? We have a storage layer that's consistent across multiple data centers. If a yarn in one data center were to fail, that data center where the data was ingested, we can't run it there. But in a little while, that data will get replicated to other data centers. And we are aware of that. We can run the job in the other data center post-replication. So in this failure scenario, the user is not really intervening to make it work. We can run the job in the data center when the data shows up, and he'll eventually get his answer. It may be delayed because the data center failed or the yarn in a data center failed, but surely the job will complete and it will produce accurate results. For every yarn transaction or Paxos? In a 2-stage manner. The metadata is replicated synchronously using Paxos, and the data itself follows because we ingest the data in the data center of origin completely, and then we push blocks to the other data centers. The data is written in the data center of origin, that's correct. And that's very similar to how HDFS normally works, right? If you have a HDFS client that does a create file and then starts writing data, if you have another client come in, it can see the file because the create file has succeeded. But if it tries to read the data, it'll find 0 bytes because the client may not have flushed it or may not have closed, the writing client may not have flushed or closed the file. So we've just extended that concept to a different data center. It takes more time. Now, we want to get really clever at the compute layer. We know where the data is, so we want to run the jobs there. But the replication is happening in the background all the time. That's one more point why we say we use the bandwidth more optimally than a solution like DiskCP, which needs spiky, very high bandwidth links. Go ahead. Paxos is mathematically strong, and like any mathematically strong algorithm, it's not a trivial exercise. Even Zookeeper and Raft and all those things are trivial compared to Paxos. It's hard to implement, but it's very fast when implemented right. It has a lot of opportunities for speed improvements that folks at Google and Microsoft have talked about. We implement a lot of those. We've also extended it to work over the WAN. So our Paxos, there is no performance penalty to using our file system over stock HDFS. In fact, you benefit from some ones which are very intensive on the name node because you now have 3 name nodes servicing the clients. Alto store, right. So, go ahead. We have a thin layer in front of the stock HDFS name node, and we have 2 more instances of the name node. As you probably know, the name node can be set up only in active standby. We have 3 active name nodes, and we have a thin layer. Ours is an RPM that installs on the same name node machine, and we coordinate the requests before they hit the name node. That's the simplest way of describing it. And if you're using the same version of Hadoop in all of your data centers, then this is a perfect solution. If you have requirements for using EMC Isilon alongside in one data center and Hadoop in another data center, but you want to use your Hadoop applications on top of both, then we would ask you to use AltoStore, which also uses a Paxos-based metadata coordination and a follow-up data transfer process. But the advantage of this is you can have different types of file systems. So it's your choice.
And only the data that we written using the AltoStore /URI gets replicated, or
Correct. So you can replicate different data, different subdirectories to different data centers. You can have DC1 and DC2 replicating /REPL1, and you can have DC1 and DC3 replicating /weblogs, and you can have a different combination of replicated folders. You ingest into one, and you can do interesting analytics on that. I have a few more minutes. I will run through quickly one interesting example. This is somewhat of a future. This is a product that will be coming out in the latter half of this year. But I want to show you the possibilities of having such strong coordinated data available in different data centers. This is a standard weblog processing system that I use for my experimentation. Let's say you have 4 data centers, US East, West, Europe, and Asia, and you're ingesting into each of those using Hive. Here's a table definition that I've been using for a while. It's just a table that takes web logs and ingests into US East in the US East data center, and each of those 4 data centers are ingesting into 4 different places. They're replicated. Now, let's say you ingested 60 gigabytes, which was the web logs for the day. Replication starts. WAN links have latencies and bandwidth limits. That 60 gigabytes is going to take some time to replicate. Now, if you were to run a query to find out all 404 requests, using a subset table of this kind. Let's say you're inserting into that table using this query, insert override table, US East 404, and submit this job to DC-aware yarn. Now, we know that the USD's data center is where the 60 gigabytes was ingested. We know that's where the data is. That initial MapReduce job will be run in that data center. So the 60 gigabytes gets knocked down. It may be 1 or 2 gigabytes. The interesting capability we have in our storage is we can prioritize the replication traffic so that the results of this MapReduce job get replicated first before the raw 60 gigabyte web logs, which is also something you want to replicate. Eventually, for disaster recovery purposes, you want the data available everywhere. But the nifty thing is, because we prioritize this, you can run an aggregation Hive query in a data center of your choice, maybe the one with the most capacity or the least utilization, much before all of the 60 gigabytes from US East and maybe 40 gigabytes in US West and everything else gets replicated to one hub, if you will. So this shows you the power of being able to do strongly consistent storage along with very intelligent scheduling of where the jobs are run. Your application authors do not need to worry about location of data. They're just writing Hive queries as always. Your Hadoop administrators do not need to worry about keeping distcp up and running. You'd need an army of distcp administrators if you want to run 1,000 applications on distcp-based systems. You avoid all that. You have a single storage system. Take your pick, nonstop HDFS or AutoStore. Will keep the consistency requirements very strong once you establish the policies. After that, your users can write regular Hive jobs. Jobs will get run where the data is available. Results will come out faster than trying to replicate everything into a hub data center of some sort. So with that, I want to open this up for questions. If you can come up to the mic. Correct. So this goes back to the first point I made. You really cannot run mappers across 4 data centers, have reducers in one or distributed also, because each reducer needs to talk to each mapper's results. As the other gentleman pointed out, the mapper may be done, the results may be stored on local file, or the mapper may still be alive. But the point is that each reducer has to talk to every mapper to collate that result. That really doesn't work well over the wide area network. But if you look at it, if you submit a Hive query, it's going to turn into 5 or 6 MapReduce jobs. As the data goes through its pipeline, we'll replicate the results much faster. So you'll get utilization of the other nodes in the cluster because other jobs will get run there. And overall utilization will be up. If you remember, it's an active-active system. So if there's just one application running one query, then sure, you can tell me that it's running on one data center. But if you have a few hundred users running 20, 30 applications, all of your data centers will get active and be very highly utilized. For that unit of granularity, which is that MapReduce job, it has to run within that data center. There is no escaping that. I mean, we're not offering you solutions to the laws of physics. You can't do that. Yes. So again, this is a choice we made based on, there is no underlying technology reason why we can't let it run, but most of the applications that we're encountering at our customer sites have different requirements. And for your particular case, the Amazon S3 thing sounds like a really good solution. Replicate your data to S3, fire up 2,000 VMs there, they run for 30 minutes each, you're paying just for the 1 hour. And you get, you have your local data center with just 20 machines. You can get a lot of work done for your dollar. No. The data ingest finishes within that data center. This is what I meant by making the client be very robust. So once the data is written and the client closes the file, that pipeline closes in that data center. He gets acknowledgement that the data has been written. He goes off to do other things. In the background, as each block is completed, we're pushing blocks over the wire, over the WAN to the other data center. I'm sorry, I didn't follow.
Basically, this is why you are doing this new stuff. So when you run job on both sides, like you use both yarns are still alive.
Yes.
So when you run job on one side, you get one set of data. Run job on another side.
No, we know that the blocks are not replicated there yet. So we'll run the job on the site where the data is available. Because we know that unreplicated blocks are there. We can look in our file system, you can look at a directory and ask for how many foreign blocks are present. We have admin interfaces for those. And we use those admin interfaces to say, this is a MapReduce job with this set of input directories. Let's look at those directories, how many unreplicated blocks are there or foreign blocks are there. If there are no foreign blocks, fine, run the job there. If there are foreign blocks, you can come back later to see if the foreign blocks have been replicated in. Otherwise, we will not run it on that data center. For policy reasons, you may have no replicas of that file in this particular data center at all. In that case, the job will never get scheduled there because we will not find that data. No. Application does not need to change and it does not need to be aware of anything. It's completely taken care of by our storage layer, publishing interfaces, and our compute layer talking to the storage layer to find out where the data is available. Such as Hive Meta Store. We have alternate solutions in the works for the Hive Meta Store. As you know, it's not a HDFS thing. It stores it in MySQL or PostgreSQL. We have out-of-band mechanisms for replicating that data. You could also make the claim that Hive is storing in not Hadoop thing, which is what we want to offer a unified solution, right? I mean, customers such as yourself or your customers will not want to know the details of what techniques we're using for replicating what. At the end of the day, if we say nonstop Hadoop runs over multiple data centers, all of the components of that will be replicated in the right places. For Hive and other non-Hadoop database solutions, we have out-of-band mechanisms. HDFS is what I described earlier, but all of them are consistent. Our core technology, remember, is strongly consistent replication across the WAN. We follow the same principles. We use the same technology for every replication we do. We have a beta version of our Hive metadata replication in specific POCs. And if you have interest and you'd like to participate in that, we're happy to show that and work with you. Yeah, we do. We take care of all of that. And the management console is integrated with Cloudera Manager or Ambari. So all of those are well integrated, smooth flowing workflows. There's no issues there. If a new application comes up that needs to replicate some other database, we'll attack that also. At this point, Hive is the one that we're doing. So the Hadoop administrators do need to be aware of all the data centers and all the machines in the data centers. The application authors do not. They just submit their jobs, and the jobs will get run where the data is available. It's completely transparent to the application authors. It's different Cloudera managers for the different data centers. So if you have 3 data centers, you'll have 3 Cloudera managers. And we have an add-on to the Cloudera manager that manages our nonstop HDFS components. And you'd add those. And we have our own management console that goes from this, and it helps you manage the whole cluster of name nodes. You should come by our booth. We have a really good demo of the management pieces. All right. I think I'm out of time. Thank you all for taking the time to come to my talk.